Hello everyone. Today we are going to discuss two problems related to Fourier series from the interval minus pi to pi. So the first question goes like this. Obtain the Fourier expansion of f of x equal to 1 by 2 pi minus x in the interval minus pi to pi. So the given function f of x is 1 by 2 pi minus x. So you have to put x as minus x, then substitute it 1 by 2 pi plus x, which is clearly not equal to minus of f of x. So this is not an odd function. Also this function is not equal to f of x. Here see 1 by 2 pi minus x, and this is pi plus x. So this is clearly not equal to minus f of x, also f of x. So this function is neither even nor odd. Write it down. So in this case we need to find all the Fourier coefficients, that is a0, an and bn. So let's find out all of them one by one. a0 equal to 1 by pi minus pi to pi f of x dx. So substitute the value of f of x, 1 by 2 pi minus x dx. So bring this 2 outside, it becomes 1 by 2 pi minus pi to pi minus x dx. So now integrate this function, that becomes pi x minus x square by 2 from the interval minus pi to pi. So now substitute the limits, that is pi square minus pi square by 2 minus pi square minus pi square by 2. So in the place of x we need to substitute the limits, that is pi into pi becomes pi square minus x square, you have to substitute pi square by 2 minus the lower limit minus pi square by 2. So let's simplify this. Pi square by 2 plus 3 pi square by 2. So you have to take the you have to multiply this. 2 pi square minus pi square by 2 will give you pi square by 2, and minus 2 pi square minus pi square by 2 will give you minus 3 pi square by 2 into minus. So minus into minus becomes plus. Simplify. Two ones are, two twos are, 1 pi gets cancelled and 2 gets cancelled. So a0 is equal to pi. Yeah, so now let's find an. Substitute the value of f of x, 1 by 2 pi minus x cos nx dA. So let's continue. Bring 2 outside. So now use the Bernoulli's rule here. So there are two functions, right? So the Bernoulli's rule goes like this. First function into the integration of second function minus the differentiation of first function, differentiation of pi is 0 and x is 1, minus the integration of integrated function, that is minus cos nx by n square. So an is 1 by 2 pi minus x sine nx by n minus cos nx by n square. So 0 minus 1 is minus 1, so minus into minus plus, so plus 1 into minus minus, so plus into minus minus, so minus cos nx by n square. Now substitute the limits, 1 by 2 pi. So pi minus pi is 0, right? So this whole function we can neglect and we can write it as 0 minus cos n pi by n square minus pi minus of minus pi, that's pi plus pi, so it becomes 2 pi. So let's simplify this. Minus cos n pi minus 2 pi sin n pi by n minus cos n pi by n square, 1 by 2 pi minus cos n pi by n square plus 2 pi sin n pi by n plus cos n pi by n square. So we know the value of sin n pi, that is 0, so this whole function becomes 0, and this gets cancelled, minus and plus, so the whole term becomes 0, therefore an equal to 0. So now let's continue. So now let's find bn. Take 2 outside, pi minus x dx. So again use the same Bernoulli's rule. First function, integration of second function, that is minus cos nx by n, minus differentiation of first function, that is 0 minus 1 into sin nx by n square. From the interval minus pi to pi. So let's simplify this. Minus cos nx by n minus sin nx by n square. So again the same thing, 0 minus 1 is 1, so it becomes plus 1, so here it is minus, sorry, so this becomes minus sin nx by n square. So now let's substitute the limits first. So pi minus pi is 0, I'll directly write it 0 minus sin n pi by n square minus 2 pi minus cos n pi by n plus sin n pi by n square. Let's continue. Minus sin n pi by n square plus 2 pi cos n pi by n plus sin n pi by n square. Here these two terms gets cancelled. The value of cos n pi is minus 1 to the power n. So now let's substitute that. 2 pi minus 1 to the power n by n. So here the same thing, 2 pi gets cancelled, so the final value of bn is minus 1 to the power n by n. So now we have found out a0, an and bn. So now let's write the Fourier series. F of x equal to a0 by 2. So the value of a0 is pi, so pi by 2 plus an is 0, so we can neglect that term. We'll directly come to bn, summation of n equal to 1 to infinity minus 1 to the power n by n sin nx. Yeah. So this is the required Fourier series for this question. We'll get to the next one. So yes, this is the next question. Obtain the Fourier series if f of x equal to x square over the interval minus pi to pi, and we have to deduce these three cases. So the deduction of these three cases goes as follows. So after we get the Fourier series, right, we need to substitute the values of f of x, like we have to substitute the values of x over there. So the values of x goes like this. First we need to substitute x equal to 0. By substituting x equal to 0 and by splitting the Fourier series for the first function, we'll get this proof. In the same way, for the second function we need to substitute x equal to pi, and for third function either we can substitute x equal to minus pi, or we can add these two functions. By adding these two functions we will get the third function. So now let's do it. First step, f of minus x minus x whole square, that is equal to x square. So clearly we can see that f of minus x is equal to f of x. So therefore if this f of minus x is equal to f of x, therefore then it is an even function. So in case of even function we know that bn equal to 0. So now let's find an and a naught. So first we'll find a naught. The formula is 2 by pi 0 to pi f of x dx. So let's quickly find a naught. 2 by pi 0 to pi f of x is x square dx. A naught equal to 2 by pi. The integration of x square is x cube by 3 from 0 to pi. Substitute the limits. 2 by pi cube by 3 minus 0 cube by 3 is 0, so I am not writing that. So cancel one pi term. So a naught equal to 2 pi square by 3. Okay. So now let's quickly find an. Minus pi to pi cos nx dx. So an equal to 2 by pi 0 to pi, sorry, this is 0 to pi x square cos nx dx. So an equal to 2 by pi. Again same thing, we need to use the Bernoulli's rule. First function into integration of second function sin nx by n minus the differentiation of first function, that is 2x, into the integration of the integrated function. Again, so this goes on. So after minus I said that this will become plus. Then again the differentiation of 2x is 2 into the integration of this function is again minus sin nx by n cube 0 to pi. Let's continue. Pi square sin n pi plus 2 pi cos n pi by n square minus 2 sin n pi by n cube minus 0 into sin 0 by n minus 2 into 0 into cos 0 by n square minus 2 sin 0 by n cube. So we can see that all these terms get cancelled. 0 2 into 0 0, so sin 0 is 0, so all of them gets cancelled, only the upper part is remaining. So now let's do it. Pi square, so we can see that sin n pi is 0 plus 2 pi The value of cos n pi is minus 1 to the power n by n square minus 0. Sin n pi is 0. So an is 2 pi by n square. So pi gets cancelled. So an equal to 2 into 2 4 by n square. So this is the final value of an. So we know that bn is 0, so directly write the Fourier series. So the value of a0 is 2 pi square by 3 and a0 by 2, so it becomes 2 pi square by 6, that is equal to pi square by 3 plus summation of n equal to 1 to infinity by n square cos nx. So there is no bn term, so this is the Fourier series. So now after this we need to do the proofs. So the first case proof is we have to put x equal to 0. That becomes f of x function. We know that in the question it's given as x square. Substitute it. Pi square by 3. We need to remove this summation and you have to split the functions. So in this function 4 is common, it's constant, so we can take it outside and substitute the values of n. So minus 1 to the power, so n tends to 1 to infinity, right? So you need to start from 1 by 1 square cos x plus minus 1 to the power 2 by 2 square cos 2x, and this goes on. So now we need to put x equal to 0, that is x square 0 square is 0, pi square by 3 plus 4 into minus 1 to the power 1 by 1 square cos 0 plus 2 square, again cos 0, cos 2 into 0 is 0, so again cos 0, this goes on. So bring this pi square by 3 to another side, it becomes minus pi square by 3, 4 into, so cos 0 is 1, so multiply it, it becomes minus 1 by 1 square, minus 1 square is plus 1, plus 1 by 2 square, again the minus 1 cube is minus 1 by 3 square plus 1 by 4 square, goes on. So now bring this 4 to the denominator, minus pi square by 12 equal to minus 1 by 1 square plus 1 by 2 square minus 1 by 3 square, this goes on. And now we need to remove this negative sign. So but to remove this negative sign we need to multiply negative sign on both sides, so this becomes minus into minus plus pi square by 12, and by by multiplying the negative sign we get the signs get interchanged. So this is the first proof. We proved that in x equal to 0, the first case, that is pi square by 12 equal to this series. So now we'll prove the second case. In second case we need to put x equal to pi. So let's substitute x square, right? So pi square by 3 plus 4, take it out, common, minus 1 to the power 1 by 1 square cos x, right? So cos pi plus minus 1 or 2 by 2 square cos 2 pi, this goes on. So the value of cos pi is minus 1. So substitute it. Minus 1 to the power 1 is minus 1. Cos pi is minus 1 by 1 square plus minus 1 square is plus 1, and the value of cos 2 pi is plus 1 by 2 square plus again minus 1 cube is minus 1, and cos 3 pi value is again minus 1, 3 square, and this goes on. So now bring this pi square by 3 to another side, that is pi square minus pi square by 3 equal to 4 into 1 by 1 square plus 1 by 2 square plus 1 by 3 square. So this becomes 2 pi square by 3, and let me bring this 4 to another side, that is 4 into 3 becomes 12, 2 pi square by 12, 2 square plus 1 by 3 square. So we can cancel this, pi square by 6. So this is the second proof, pi square by 6 equal to 1 by 1 square plus 1 by 2 square plus 1 by 3 square, and so on up to infinity. So now we'll do the third proof. So in third proof, as I said, that we can either put x equal to minus pi, or we can add the two previous proof that we have proved. So if we put x equal to minus pi, we'll get the answer, but that takes a bit long. So now let's directly add these two proofs that we have done. That is, on the left hand side it is pi square by 6 plus pi square by 12 is equal to 1 by 1 square plus 1 by 2 square plus 1 by 3 square up to infinity plus 1 by 1 square minus 1 by 2 square plus 1 by 3 square up to infinity. So now let's simplify this. This becomes, while we take LCM, I hope all of you know it, so I'll directly write the step. It becomes 3 pi square by 12 is equal to, so here we can see that 1 by 1 square and 1 by 1 square, there are it's adding up twice, so we can write 2 into 1 by 1 square, and on the other case all the even terms, right, like from 1 by 2 square, 1 by 4 square, all get cancels each other. See, in this case it's 1 by 2 square, and in the other series it is minus 1 by 2 square, right? So those two gets cancelled, and the same way all the even terms will get cancelled each other, and all the odd terms will be multiplied by 2. So now let's write it, 2 into 1 by 1 square plus 1 by 3 square plus 1 by 5 square. In all the cases, all the odd terms are repeated, like see, 1 by 1 square plus 1 by 1 square, 1 by 3 square plus 1 by 3 square. So I just took 2 outside and I wrote all the odd terms. Same way, bring this 2 to the denominator, 12 into 2 becomes 24 equal to plus 1 by 3 square plus 1 by 5 square, 3 ones are 3 8s are. So we got the third proof as well. By adding the previous two equations, we even got this third proof. So that's all for today. Hope you enjoyed this session, and we'll be meeting soon in the upcoming classes. Thank you.